All right, good day, everyone. Today's lesson is going to be the second portion um, of our 17-2, which is going to be the fundamental theorem of algebra. Okay. In this lesson, we're going to kind of switch up our math and kind of go a different route of how we actually solve out examples. So, in the first half of this, we talked about factoring, getting our answers, getting x equals a specific value. Well, now we actually want to work backwards to see if we could actually solve out for the original polynomial. Okay. So if you notice up here in this example, notice how they give you three different zeros, and then they set up each of them as a factored form, and then they basically FOIL it out or distribute all those values through. Okay. Well, that same process is going to be what we take today. Okay, but there's a couple of key things you need to understand. First off, in a problem like this value right here isn't actually a zero. Okay, notice how it's completely separate from the zeros values next to it. This is actually our degree. And the reason it's important is kind of like how we talked about yesterday. It actually tells you how many answers you should have. Now, in this problem currently, it's not really going to matter. Okay? And what I mean by that is it's really not going to tell us anything in this first example. It will eventually, but it's really not that important right now. What is important, though, is these three values here. Those are my three zeros. And the big thing you have to understand is that those values are basically like saying your x value each equals those individually. But I don't want them as x equals. I want them as factored forms. So what I need to do is I basically need to move all these numbers over to the side of the x. Well, I would do this by respectively doing addition or subtraction based off what the number is. I would subtract 0 to get x minus 0. That would be one factored form. I would subtract the 5 to get x minus 5 as my other factored form. And I would add the 7 to get x plus 7 as my last factored form. Okay? At this position, if I were to simplify this, because I really don't need an x minus 0, I would have x times x minus 5, x plus 7. Okay? So notice how I took my original zeros and worked it to this point where they're all a factored form. The last step of this is going to be basically what we have been doing for months now. We have to distribute those values through. So what I'm going to do is I'm basically not going to worry about this x just yet. I'm going to FOIL out these values to start with to see what I actually get as an answer. Well, I would do x times x and x times 7. That would give me x squared plus 7x. Then I would do negative 5 times x and negative 5 times 7 to get negative 5x and negative 35. At that point, I can simplify the 7x and the 5x to get x squared plus 2x minus 35. Okay? And that's what happens when I FOIL out those first two values. The last step now is I have to bring down this x and now multiply this value through that equation. Okay, so now all it is distribution. I would multiply the x to all three of these, work it out, and get to my final answer. That would be x cubed plus 2x squared minus 35x. And I have my original polynomial sitting right there. Okay? So the key thing to understand about this lesson is they're actually giving you the answers that we were looking for in yesterday's lesson. Okay, they're giving you the zeros. The difference in today's lesson is that we're actually working the other route. We want the original equation, so we FOIL everything out and multiply it. So let's look at our second example, because there's obviously more to this, especially with that degree value that they give you at the beginning. Well, one of the things you have to understand is that there's actually a fundamental theorem in algebra that basically states that if you have an imaginary number, that if you have one value of the imaginary number, then you need the other. For example, if you have one of the zeros, let's say one of the zeros is 2i, okay? Well, because 2i is an answer, you can automatically assume that negative 2i is also an answer to that problem. Okay? Take that vice versa. If negative 2i is an answer, then you can automatically assume that positive 2i is also an answer. So one of the ideas is that anytime you have an imaginary number, you need both the positive and the negative values. The reason that's important and the reason why it kind of goes back to the degree is because you'll get problems similar to this in letter A. Notice how your degree is 3. Well, that should tell us we should have 3 zeros in this problem. The thing is, though, when you first glance at this, notice what happens. You have x minus 2 and x equals 3i. We're kind of missing a third zero, right? They only tell us 2. Well, this is where that degree value becomes important. It's basically telling you, like, hey, hold up, we have to find the last one. Well, the last zero is just the opposite of that 3i, or negative 3i. At this point, now that I've completed all that, I can start working it out just like I would in the other example. I can rewrite this as x plus 2, because I would add that negative 2 over, x minus 3i, and x plus 3i. At this point, I just have to start multiplying values out, basically foiling. Well, I always like to start with the two imaginary numbers first because eventually things should cancel out. So if I multiply the x to both of those, I would get x squared plus 3. Remember how we talked about this earlier in Unit 2. It's 3ix. Looks very strange. Negative 3i times x, negative 3i times x. And then negative 3i times positive 3i becomes negative 9. And then I times I is I squared. Kind of going back to when we used to have to multiply imaginaries together. Well, in the middle here, we have 3ix, negative 3ix. Those are going to cancel each other out. And then if you remember, I squared disappears, but it flips our sign first. Okay? So the I squared is going to flip the sign and then disappear. So this becomes x squared plus 9. Okay? Now after that, I just need to bring down the x plus 2 and then just rinse and repeat. So now I do x times x squared, x times 9. That would give me x cubed plus 9x. 2 times x squared, 2 times 9 would be plus 2x squared plus 18. And so at this point, I look to see if I can simplify or combine anything together. Unfortunately, there are no like terms there. So let's just write into standard form, x cubed plus 2x squared plus 9x plus 18. And I have my final answer right there. Okay? So notice the math of today's lesson, the actual math itself, is really just foiling. Okay? Things that we've completed in class before, things that we have actually done throughout the year. Okay, we've gone about and foiled polynomials, we've foiled imaginary numbers, we've done all this stuff. The difference of today's lesson is truly understanding how to take information like this and apply it to our answer. Okay? On top of that, understanding that if I have a complex root or an imaginary one, if I have one answer, that I need to have a second one. And that second answer either has to be the opposite sign of the original. So for example, once again, if I have a positive 3i, then you must have a negative 3i also in that problem. Okay? Besides that, go ahead and answer the questions on the Edpuzzle. If you have any questions, make sure you bring them to class. And I will see you tomorrow.